Hello everyone, welcome to this series which is on machine learning fundamentals, and we are on a very important topic today, that is handling imbalanced data in machine learning. We had taken earlier, in fact, some of the important concepts that are related to various parameters that we are using. In fact, after a random forest, we had in fact talked about different parameters that are very important as far as machine learning is concerned. Continuing to that, it is very important in machine learning that we should be able to handle the imbalanced data. I'll be showcasing you first that what is the impact if we are not able to successfully handle the imbalanced data. What are the repercussions it can have, and it can make in certain instances or use cases, it will be making machine learning useless if in case we are not able to handle the imbalance in the data which is there. Moving on this, let me just directly go to this concept. I want to wrap it up, fast. What is first of all imbalanced data? Imbalanced data occurs when one class significantly outnumbers another in observations. So if you are having a majority class, for example, and there is a minority class, and the majority class is, in such a manner that it is outnumbering completely the minority class, in that case, we say that this is an imbalanced data. We can give examples for this. This creates challenges for machine learning models. So if such is the scenario, it can create challenges for machine learning model. Here I would like to say one thing. There are certain areas, application areas of machine learning where such things can happen, and they are very common. For example, we can take an example of a fraud detection in which we normally see that frauds, if we just take the percentage of frauds, normal transactions might be 95 to 98%, but it is just 2% of the total transactions that are happening. For example, we can just say that there are 2% maximum, or 2 to 5% of those transactions which may be fraud, because 95 of the other transactions which are there, they are the normal transactions. So when we are getting the data as well, we will see that data will be imbalanced in a manner that normal transactions will be occupying 95% of the data which is there, and there will be some of 2 to 5% of the data which will be representing in fact that minority class which is the fraud. So we can have in fact a machine learning model which will be leaning towards, or we can say, it will be facing a challenge while dealing with such kind of data, and that will be in fact the imbalance which we have to handle. So first of all, let me give a little bit more explanation to this so that you can understand it better. The example is that we are having class 0, which is a majority class, and that is having 950 samples. So this is a majority class which is there. It can be anything, but for example, class 0 is there, which is a majority class. It's having 950 samples out of 1000. And there is class 1, which is a minority sample, which is having 50 samples in total. So if we see the ratio in this particular case, it comes to 19:1, because for every 19 class 1 majority which is their samples, there is a class 0 samples, there's a class 1 minority sample which is 1. So 19:1 is a ratio which is in fact a huge imbalance in the data. So if we see real world scenarios or the problems which are there, fraud detection which I was mentioning, in fact, that is a significant one where you can have very less data that pertains to actual frauds. Disease diagnosis is one more, because tests that are conducted on patients, you might just see 95% of those tests which are there, they will be normal. Just 5%, 2%, 3% of the cases, they will be having some detection of a disease, or identification of a disease, or those samples will be those which are in fact the exact samples of disease. And in this case as well, there's a possibility that machine learning model will be in fact getting deviated towards the majority. And spam filtering is one more area in which mails are there, and you can have 98% of the meals which are normal and rest of two. Manufacturing defects in the same manner. If we have to detect manufacturing defects, because manufacturing defects are something which are very rare, so you might be having 100 samples, out of which one, out of 100 samples you're having one which is defective, and 99 will be normal. So it's a minority class which results in data imbalance. Why is imbalanced data a problem? Why it's a problem? We will say why it's a problem. Machine learning needs minimize overall error. So we know that machine learning, machine learning is meant for that. That we want to minimize the overall error which is there. It causes, definitely it will be causing a bias towards the majority class. So when a machine learning model is learning, when it's learning, there will be a bias, natural bias created towards the majority class, because it is available in majority. For example, from 1,000 samples, 50 fraud, 950 are non-fraud. So we are, even if, for example, a model predicting all as non-fraud will be getting 95% of accuracy. Even if, for example, model is saying, because we'll say that it will be getting biased towards the majority class, which are for which the chances are higher. So what will happen is, if it is detecting, or it is designating or predicting all 1,000 as non-fraud, it will still get 95% accuracy. So here accuracy will not be this 95% the accuracy, but it will be detecting the zero cases of fraud, and model usefulness which is there, that will be none, it will be zero. So even if we have implemented this machine learning model, the model accuracy is 95%, but the usefulness is zero, because it is same as we are getting, because 95% of the cases otherwise as well. So we are having accuracy of 95% directly. So machine learning model is not doing anything in this case. Business impact, missed fraudulent cases which are there. So we'll be having a huge impact in this case as far as business impact is concerned. So this will be a model usefulness is nil, it is zero, it is useless. And undetected disease in medical diagnosis, that can be something which is very it's having a lot of implications. That is one area in which implications can be huge. And then failed quality, you'll be having quality control, failed quality control in manufacturing, where it will not be able to identify those defects in manufacturing for which this has been intended. Because if you are having 98% of the manufacturing without, or 99% of the manufacturing without defects, so how a model will be able to predict that one which is there, because it is majority class is which is having no defect. So in such a case where imbalance of data is a huge problem, and it is in fact leaving a machine learning model useless, because there is no need for implementation. If this is the scenario in a lot of various use cases or scenarios, as we have pointed out, then it will be useless to implement a machine learning. So that is why imbalanced data is a huge problem, and we need to take corrective measures to actually address this problem. It is very important. It is not just that implementing and deploying machine learning model is a problem, or training a model, testing a model, training a model. This also is a huge problem, and in certain situations, certain scenarios, will not be able to utilize machine learning if we are not addressing this problem. So, visual intuition of class imbalance. The visualization demonstrates how imbalanced data affects model learning. So definitely when we are visualizing, so this visualization will be in fact giving us the imbalanced data, and affects how it is impacting the model learning. We notice that the majority class forms dense clusters, while the minority class, so if you can just see this on the left hand side, so majority class is there on with the blue, and minority class is with a different color. You can just see It is with a orange color there. So you're having an orange and minority class with an orange point says sparse and scattered. So you can just see on the left hand side, if you just see here, it is pointing out this is the majority class, which is with the blue, and the minority class, which is here shown with the orange. So are the sparse and they are scattered. So this majority class is there, and it is forming a dense cluster, whereas minority class is sparse and scattered. The decision boundary becomes heavily skewed towards the majority class. Definitely that is there, causing the model to learn majority patterns. So you can just see it's heavily skewed towards the majority class. We can just see it from this diagram here, which is there. You can just see visualization, which is here. So from here we can just see this, that it is skewed towards majority class, causing the model to learn majority patterns, while it is effectively while effectively ignoring the minority class. So this class which is there, the minority class, it is getting ignored. So this is in fact the visual intuition of class imbalance. You can just see that. And then definitely we have learned up till now that class imbalance, what that is, why it is a huge problem, what is the reason that class imbalance is a huge, it is a huge problem, why it is a huge problem. We have just showcased that in case you are not addressing the imbalance of the data, it might render your machine learning useless in many of the scenarios which we have provided. So there are types of imbalances. Mild imbalance is the one. So mild imbalance is, for example, 60-40. So that we can just say it's a mild kind of imbalance. So between the classes, generally such kind of imbalances are manageable. You can have minor adjustments in algorithms, certain other things may improve the performance, that we have in fact taken into consideration before as well. We have discussed that. But there is a moderate imbalance, which is again 80 to 20. So minority class will be 20. So this is a moderate. It requires attention. Standard models begin to struggle. So our sampling techniques are recommended in this. So we are having various oversampling techniques that can be in fact used to address this moderate imbalance in data. But there can be a severe imbalance, sorry, in the data. So that is 95 to 5, which we have discussed. In fact, this is a worst ratio critical challenge. It requires advanced techniques like SMOTE, which is synthetic minority or sampling technique, or it might be requiring an ADASIN for effective minority detection. So we are going to discuss both of these techniques in quite a detail. So probably maybe in this particular episode or the following one which is there. So you can just see this types of imbalance. We are having mild imbalance that can be handled very easily. So we might have to just do certain adjustments here and there, maybe in algorithm itself, and then that can be handled. There's a moderate imbalance which is not handled, in fact, directly. It requires some oversampling technique. And then we are having a severe imbalance, which is not handled by a standard or sampling. For example, random or sampling, or it is not handled by that. We need a specialized kind of or sampling technique like SMOTE or Edison, and then that can be handled with these. And we are going to discuss all of these techniques probably after this. Why traditional metrics fail? So probably this might be the last slide. In fact, by the end of this, not this particular, I would leave it on this particular slide, and then we'll be discussing a few more parameters. But by the end of this particular episode, which is probably 14 if I'm not mistaken, so by the end of it, we'll be having a second video as well. So I want to just keep it from 8 to 15 minutes, or lesser than 15 minutes, or something near that, so not more than that. So we'll be discussing a few more parameters, and then it will be followed by a program which will be on all of these things. It will be showcasing imbalance in the data and how that is impacting the results and how we can correct that with different techniques of yeah, these oversampling techniques that are there, and then how we are able to grasp the optimum appropriate results. So coming back to this, why traditional metrics fail: accuracy, misleading, and imbalanced data sets. So that's definitely there. When you're having an imbalanced data set, accuracy will be misleading. A model predicted all majority class achieves high accuracy but fails completely. So we have seen that example in case of fraud detection. Although the accuracy of the model is 95%, this is normally what we are expecting, from a normal scenario. If it is there, we expect that 95% of the accuracy is considered to be a good one. But in case of fraud detection, it is a complete failure of a model which is having 95% of a normal data coming, and maybe probably 2 to 5% of the data which is a fraud. So in that case, the model usefulness is nothing. It is zero. So precision needs context, can appear high while ignoring minority class entirely. So you might be showing that precision is there, but precision has a context. Where you are giving a normal data which is 98% and your model is giving 98% of accuracy by just going with a majority class. If you just see that, then it is actually not within the context. It is out of context to say that the precision of this particular the accuracy of this particular model is 98% or 95%. So accuracy has a context. Recall crucial for minority detection. So definitely measure actual positive capture rate, F1 score, balance, precision, and recall for meaningful evaluation. So we don't have to go with a single parameter out there. We have discussed all of these things. What is recall? What is F1 score, AOC, ROC? All of these parameters we have discussed earlier in the previous episodes. Measures model discrimination ability across thresholds, AOC, ROC. It was a last discussion itself. And the confusion matrix essential for detailed performance breakdown. So we cannot so this traditional matrix definitely that fails. Accuracy can be misleading, and these precision will be having a context. We cannot simply take it. So crucial recall is crucial for minority detection. Measures actual positive capture rates. So if we see all of these which have been mentioned there, this can be said as this is a traditional matrix, and that fails when it comes to data imbalance. I will be leaving it here with this, and I shall be taking few more concepts in this imbalance, data imbalance, and how we can rectify it with different techniques that we're having, or sampling techniques. We are going to discuss them one by one. I'll be taking a practical portion by the end of that particular video, which is going to be a part B of this episode 14. Thank you so much once again for joining, and I hope this particular video, this particular series overall is giving you some benefit. And if it is so, please subscribe to the channel, and press the bell icon, and you'll be getting, whenever a new video is uploaded to the series, you'll be getting an intimation for that. And in case you're having any feedback, your feedback is very valuable for us. It can be critical, there's no problem in that. You can just express yourself freely. Whatever suggestions you are having, critical suggestions, so they are very beneficial for us, so that we can improve this series and other series that are coming on the channel. Thank you so much once again for joining us.